All right, thank you for having me here today. My name is Nicholas Bira, and I'm presenting a low-cost 3D printed magnetorheological flute clutch utilizing electropermanent magnet arrays. So there is an increasing trend of magnetic materials in soft robotic applications in the past few years. Electromagnetic fields are commonly used in actuation strategies in sensing and logic for rigid robots. Magnetic smart materials are particularly well suited for expanding this set of soft robotic mechanisms to bring them into parity with rigid robotics. Magnetic soft robots are often constrained by equipment such as MRIs or Helmholtz coils, and reaching that goal of untethering our soft robots from our systems requires embedding some of these magnetic interactions internally. Low power is also an important consideration for extended untethered operation. Electromagnets are great for embedding these interactions internally, but they're relatively high power. Permanent magnets also do a good job of generating large fields, but they require manual manipulation or some kind of actuation to use effectively. This brings me to electropermanent magnets, or EPMs. EPMs consist of two magnets in parallel. When they're magnetized in the same direction, they generate a net flux around the device that allows you to have an on state. If you invert the polarity of one of the magnets with a pulse of current, you're able to then contain the flux within the system and have an off state. An additional smart material to use with this device is magnetorheological fluid, or MRF. In MRF, it contains a bunch of magnetic particles embedded in a carrier fluid like oil or water. And with the application of a magnetic field, the particles align along the direction of the magnetic field and form these sort of chains that cause the viscosity or the shear behavior and yield stress to change. Combining these concepts together, we can make a MRF EPM clutch. In this design, with the area shown in blue, you can see these fins that rotate around a central shaft. And as they do, the fluid itself, the MRF, circulates around that. With the EPMs around the perimeter, you can selectively apply a magnetic field in discrete areas and control the overall yield stress of the fluid and affect the transmitted torque. Here's a picture of the EPM design consisting of a N42 grade magnet, a Alnico 5 magnet, and a coil winding. By applying a short pulse of current, you can change the polarity of the Alnico 5 magnet up or down and generate a field within the air gap on or off. This is a magnetostatic simulation of the EPMs. As you turn on more and more of the EPMs in this circular orientation, you generate about 50 to 60 millitesla within the region that's close to them. When they're all on, they generate a net value of about that much around the entire perimeter of the circle. This is the same simulation, but now adding in magnetorheological fluid in the geometry that it would have within the clutch. You can see that for all of them being on, the average value within the fluid is about 100 to 110 millitesla. And as you go out to the edges of the interior, where the cross-sectional area is a lot smaller, it increases up to about 180. This data was collected with the data I'm going to show you is collected with this device here. We built a rigid frame with a stepper motor rotating at about 50 RPM. The base is a force torque sensor measuring the transmitted torque from the shaft to the body of the EPM clutch. And the EPMs were manually toggled with a switch array. So we did an analytical model of the interior of the MRF clutch with the cross-sectional area shown here on the right. The orange and green regions were modeled to calculate the amount of yield stress or the applied transmitted torque as you go rotationally around the center. The line on the far top left, the black line, is that simulated torque transmitted based on the amount of applied field. The dotted orange line represents an ideal case where we would match that by turning on our EPMs in sequence and having about 1/6 of the total desired torque being transmitted. What we observed was actually the blue line, which only gave us about 1/5 of the total expected value, but that's likely due to a variety of things that I'm happy to talk about in my poster after this. So future work, revisiting our modeling assumptions and our analytical model, improving the MRF geometry, and including some different elements to bring our magnetic flux a bit more centered, and then construct and model and control a variable damper mechanism with this device. Thank you for your time.
Okay. Hi, everyone. So thanks for having me here. So today I will talk about origami self-sustained oscillate. I'm Wen Zhong from UCLA. So before everything, I was want to introduce origami a little bit. So here's a lot of different example of origami robot. So but basically, robots create from 2D or 1D material through a cut and folding process. And then, but they usually use microcontroller or other electronic or electromagnetic components to achieve the autonomous behavior for example, like locomotion or manipulation. And then one day, a problem occurred to me like, can we actually achieve autonomy for robotics without a discrete electronic or electromagnetic components? Of course, the answer is yes. That's why I'm here. So our solution is that we try to use functional material, functional string material, and the dry material, and then we go through the cut and the fold process. Then we try to make the full autonomous material here. So I will show one of the example here. So we start with this kind of origami self-sustain oscillator. What that means is that we only need a DC current or DC power, and then we don't need anything else to make it oscillate. So you can see here, it basically composed of a bicycle beam and a supercoil polymer actuator. We combine them in a special configuration to make it oscillate by itself without any electronic control or external controls. So basically you need a DC current, that's it. And then that's kind of the motion of this oscillate. You can see here, it features a rapid snap through and snap back motion here. So you can see it jump back and forth. And then we will show with 3 examples. One is that we can directly fold the autonomous swimmer out of paper and the thread without any electronic control. We just need to supply the DC current. So you can see it can swing by itself. And it basically drive by the oscillate back and forth and make the paddle swing a little bit. And also we can show with another example, it's a Q1. So we try to design an LED and it's a special pattern. And then we use the oscillation motion to drive 2 different switch on and off. So that make the small stick figure run a little bit. And also we can increase the current to tune the frequency of the system. So you can make it looks like it's running. And then the last one is that we actually can use this oscillator to make the robot crawl using the asymmetric friction with the ground. So it can move a little bit, but it's pretty slow now. We try to improve it a little bit. And also we can make this oscillator work underwater and under high magnetic field. It means that there's a possibility we can use that for kind of exploration, navigation, and the rescue in kind of high extreme environments. And then, so I checked the schedule last night. So I saw the Camara's talk, it's called Soft for Soft Shake. And I'm kind of become a little panic. So I'm doing that, it's kind of support again. But finally I got my answer like at 2 a.m. this morning. So here's the result, like I will argue. So first we kind of extend this origami fabrication process. We can make it into control even. So previously most of people are working on structure and how to make it move like that. And now we can actually do controlling. And then our robot is pretty compliant and is electron free and is non-magnetic here. So actually you can make it work in extreme environment, including high radiation, high magnetic field. And the third one is actually this process is pretty engaging and it's pretty accessible. The robot we here is like less than $1. So it means everyone, if you can buy PET or kind of conductive thread, you can build it by yourself under my guidance for now. And then, so it's probably a good kind of tools for kids, everything for education, except the currently really popular makers education. So you can make people build stuff or origami robot by themselves and learn from that process. And the last one is actually we are working on origami logic. So we try to use this similar diagram to create logic, and then we can do computing. And then we try to plan to do integrating the sensing, logic, and also actuation all into the origami structure. So we try to hit the milestones that we put the paper theory and also the thread and put everything together. You can directly build the autonomous robot that can interact with the environment. Yeah. And yeah, that's basically my talk. And if you got more questions about the materials, I would love to see you in the processing.
Thank you very much for this great talk.
Hi everyone, my name is Jessica and I'm a second year PhD student at Penn, working with James Cole and Mark Yim. This work was presented at RoboSoft earlier this year, so all the paper and demos are out if you want to find those. So let's get started by watching Baymax as he tidies up the room. In many ways, Baymax represents the future that many of us here are working towards, soft robots that can seamlessly integrate into human-centered environments and help people in their everyday lives. In this short clip, Baymax has managed to accomplish many technically impressive tasks, covering a lot of the challenging problems that in manipulation that roboticists are working on today. Well, let's take another look as roboticists. These are all very challenging interactions that require really good perception of the target object because they lack simple and accurate contact models. Many of these tasks are so challenging for roboticists today precisely because we need much better sensing for manipulation beyond the usual tactile sensors and the end effector and vision sensors much further away. What we have is a fundamental gap in a perception pipeline that only uses vision and touch. Sorry, I'll wait for the slide to go back up. All right. We can address this gap by adding a proximity sensing modality, which can be defined as sensing within a short distance range, originating from the locations of the tactile sensors. Proximity sensing can provide the precise localization data that vision sensors lack and information about pre and post contact behavior that is difficult to predict. So here's a quick overview of related work. In the interest of time, I'll skip to the most related, which is state-of-the-art visiotactile and proximity sensors. These sensors still have a fundamental compromise, and the design will force you to choose between either tactile sensing or proximity sensing. You can't really choose both because, for example, in this sensor, you have the dot pattern that you need for tactile sensing. That's your tactile sensing resolution, but it also includes the proximity vision. So you kind of have to always balance or choose between one or the other. In our work, we present a novel multimodal proximity depth and tactile sensor. Our sensor has minimal to no interference between both proximity and tactile modalities, which leads to uncompromised spatial resolution for each one, as well as both simultaneous and synchronous proximity and tactile sensing for sensor fusion. If you think about it, cameras are just really fancy light sensors, so the optical properties of the soft membrane are really what enable the dual sensing modalities. For proximity sensing, the membrane must be infrared transparent to allow infrared light emitted by the depth camera to pass through. For tactile sensing, we need the membrane to block visible light and have a high contrast pattern so that we can observe the membrane with the RGB camera. So let's dig a little deeper for our first question, which is how does light transmission work? At the atomic scale, photons collide with electrons. The electrons can then either absorb the photon and be excited to discrete higher energy levels, or if the photons don't have enough energy, they're simply transmitted. These transmission frequencies are well defined, and as we move up to the material scale, the transmission frequencies broaden and become more continuous as atoms act on each other and different elements have different absorption frequencies. So the second question that we have to ask is how can we get this high contrast visible pattern without interfering with proximity sensing? We have two huge challenges. First, the excitation frequencies of visibly colored materials tend to extend into the infrared spectrum and block the depth camera. So you can see here on this kind of scale that 860 nanometers, which is where the depth camera operates, is incredibly close to the visible light spectrum, only within just a couple hundred nanometers. And the second challenge is that the thin layers of visible dyes don't create enough contrast for pattern detection. So our solution to this is to use phosphorescence. These phosphorescent particles are only activated by high energy ultraviolet light and don't absorb the infrared light from the depth camera, which is too low energy. And these phosphorescent particles absorb the UV light and they actually emit visible light to create this really high contrast pattern that is really easy to observe with the RGB camera. So we fabricate the membrane using a layering approach. In the first layer, we mix Ecoflex 30 with the visibly opaque and infrared transmissive dye. In the second layer, we pattern the dots with the stencil and phosphorescent ink. We use copper doped zinc sulfide. And in the third layer, we seal the dots with plain Ecoflex, which evens out the dot protrusions and makes the surface more matte. And so this fabrication process is pretty simple, only takes about 30 minutes, assuming you heat cure the last room. So here's an overview of our system. So you can see the membrane here, the internal ultraviolet LEDs, the air pressure sensor, our internal camera, which we use the Intel RealSense L515. And the sensor is integrated into an end effector and mounted on a Euro 10 robot arm. So this is a demo of the optical flow, which we use for tactile sensing. We can track the motion of the dots and you can see the direction of shear with the arrows and the approximate magnitude with the length of the arrows. We test the sensor with a data set of common objects. You can see the proximity depth map outputs as well as the tactile RGB images. And for our demo, the tasks I chose can each be split into 3 different stages. So that's kind of the key part here, where we have pre-contact, during contact, and post-contact, where the combination of the proximity and tactile sensing can be most useful. So the first task is approaching contact. So here you can see as we're approaching the nail polish model, you see the nail polish in the proximity depth map far before you get to the tactile sensing. And you can also see how it agrees with the ground truth. For catching, I slowed this down to 0.12x speed. And again, you see the Rubik's Cube and the proximity depth map far before it even appears in the frame for the camera I'm using to film, kind of like the real life analog. And finally, for throwing, I think this is where it's kind of the most interesting, where you get this really nice observation of the object behavior that you don't see in the global view. And you also see the object in the proximity depth map even after it's been released from the sensor surface. Thanks so much for your time. Please find me at my poster during the break. And I'd also like to thank my co-authors and sponsors. For our online participants, I have a QR code that goes directly to the PDF recorded talk from Robosoft and also my demo video. Also happy to take questions by email. Thanks so much.
Thank you very much for this talk. We're having some problems at the moment online, so you don't see that much of that, but we can't have a picture online.
Thank you for the opportunity to present today. I would like to promote the idea that in soft robotics, modeling benefits from a well-chosen design, and that vice versa, designing benefits from a well-chosen model. And isn't it a usual situation being either interested in a new design or in a new model for an existing design? In soft robotics, both go along with special challenges. So for the design, estimated dimensioning, for example, is very hard compared to conventional robots. And for the modeling, of course, the continuous deformation and non-linearities of the material are challenging. However, there is an interrelation between both, which is important to consider from my point of view. So if you choose the right design, you will simplify your model. And if you choose the right model, you can optimize your design. My example today is a multi-chamber bending actuator, which we typically model as a Coursera beam. And you can see the actuator here. We derived it by a systematic investigation of design parameters, which you can find in this publication. And basically, it consists of 3 chambers in parallel, which you can see here. And of course, if one chamber stretches, the whole actuator bends. And what is interesting is that we found that efficient and easy to model actuators fulfill equal demand. So due to limited time, I picked just the 3 most relevant design aspects for modeling. So one is the chamber cross-section, so the dimensions of the chamber, which has a strong influence on the linearity of stretching. The second is the reinforcement. So we decided to use rings for this design because it's easier to manufacture, but the choice of the reinforcement has a strong influence on the linearity of the stretching. And the last aspect is the connection of chambers. So you can see here that we use linking elements to connect the chambers instead of embedding the chambers into a body of silicon. Due to the design, we are able to use a novel modeling approach. Its first step is to take a look at the individual cylinders of the robot, and what we did in this publication. And you can see that the fiber reinforcement, so we have 4 different here, and the dimensions have an important influence on the linearity and of the extensional stiffness and of the stretch. The second step is superposition of the cylinders, which is only such easy due to the linking element instead of embedding the chambers into silicon. And the last step is a transformation in order to gain the parameters of the beam model. And you can see that the extensional stiffness of the whole actuator and the bending stiffness of the whole actuator depend on the extensional stiffness of the individual cylinders, which, yeah, and this is a simple equation for these parameters. So let's jump back to the first slide. As you could see, the design simplifies the model. It has an influence on the linearity and the kinematics, and implicitly it allows a modular modeling approach. And as the equations for the beam parameters are very simple, we can use the model for designing. So we are now able to estimate dimensions and deformation characteristics. With this, we solve at least parts of the typical challenges in soft robotics, which mainly come from the soft materials. And yeah, our example today was a multi-chamber actuator, but I'm sure that similar approaches will work for other robots as well, for example, for the new net. So thank you for your attention. Thanks to the DFG for granting, and I'm open for questions if we have time for this.
Yeah, thank you very much for this talk.
Perfect. So hello everyone. My name is Zhu again from Princeton, and today I'm going to talk about piezoelectric soft robot, which is able to intron, crawl, and jump, and we further optimize that with asymmetry. Oh yeah. So for soft robots, so why do we choose piezoelectric? So compared with, piezoelectric advantage is that it has very fast response, 100 kilohertz is all possible. And also it has small form factor and flexible integration. It's electrically driven, so you can integrate circuits directly on the robot, and it's still the form factor is still very small. Also, as a continuous body, it will has a whole body compact dynamic locomotion when we drive it fast. These three picture are examples. The first one is that because of this very thin, can squeeze into small gaps, and trying some search and rescue applications for inspection if there anyone trapped in a class, in a class building or something. The second one is what I really talk about is that we integrated electronics on the robot, which can convert the battery power, which can be wireless controlled and battery powered. We know piezoelectric has large voltage, but we have power converters on robot to convert that voltage to supply to the piezoelectric actuators. And it can also enable complex locomotions. So talk about the mechanism a little bit. By applying voltages, the piezoelectric actuator will extend or contract. Depends on the type of the actuators. And when we do a bilayer structure, we bond it on the steel foil substrate. By applying voltage, it will bend instead, bend up and down. I will show you some examples how much it bends, but probably like you can see about 20 or 30% to its length, vertically versus its length. And some examples. This is like a dynamic mechanical resonance. I talk about this is this can be mechanical resonance. So you can see this really bend up and down 6 centimeter for a 10 centimeter actuator. Bend up down like 60%, I will say. It's pretty much. It's very large bending for electric, for a piezoelectric actuator, and also it's electrically driven. So our robot, talk about actuator. So now we move to robot. Our robots have 5 piezoelectric actuators bonded to a steel foil substrate. And we put 2 frictional pads on the end for the motion, for the horizontal motion. I will show you that later. And the fabrication workflow, to be brief, is that we basically bond the actuator on the steel foil with epoxy, and we put the whole thing into the vacuum bag for the vacuum to press it hard on that for the bonding to be very strong. That's the basic fabrication procedure. And the next, I will show you the jumping of the robot. still it's a dynamic behavior when you drive it very fast. The jumping of the robot, you can see it's jump like in our case, it's jump at 8 millimeter high. It's actually 20 times robot thickness. The robot is around 400 microns thick. And I'll show some videos. The robot is 50 centimeter long, and it will jump up and down. The top one is extreme top. The bottom one is some simulation framework we developed. We can also see a good match between them. The square thing are just some tapes for marker process. It does not have any weight on that. So you can also do horizontal motion when you apply an asymmetric voltage. In this example, we can see it can move rightward or leftward. We can see that we only need to change the frequency of the driving. So the motion direction, both the motion direction and speed will change. This also shows that it's a complex dynamic behavior, probably related with vibration modes, related with gravity, something like that. And also the ground interaction with the ground. It has strong friction, like a frequency. So now we can see the speed is around like 10 millimeter per second or 1 centimeter per second, something like that, 1.5. And we are trying to further optimize that. We found that optimized through control voltages and optimized through the robot setup, like we need to do both. So, but for the first, to show it here, I just show our work about to optimize the motions through just adding external load to that. That will boost the motion a lot. You will see comparison like the lateral motion can go up to 6 centimeters per second. In this case, compared with 1, it's like 6 times boost. Some preliminary results probably need to optimize more, but that's a very good first step. I will show you here, and thank you so much.
Thank you very much for your presentation. Let's move on to the next presentation, and let's try to get back to the initial schedule somehow. We have now a presentation from Linda Paterno, Luigi Truppa, in person, great, Emanuele Pioni, and Ariana Machasi.
Okay, so good morning, everyone. I am Linda Paterno, a postdoctoral researcher at the Biorobotic Institute of Scuola Superiore Sant'Anna in Pisa. And today I present our work on a jamming pneumatic actuator for wearable robotics. So wearable systems such as limb orthosis and prosthesis accomplish the function they are designed for by interfacing rigid material with the limb tissues that are much softer. In addition, these systems highly compress the limb to allow for a proper and stable biomechanical coupling between the artificial device and the human body. However, this biomechanical coupling can be affected by the volume and the shape change of the limb over time, thus resulting in relative movement between the rigid interface and the soft tissues and high pressure and shear stress applied on the skin. As a consequence, the patient reports several dermatological problems that are the major causes of low satisfaction level in this field, especially in lower limb prosthesis. So in this context, our work aims at enabling a stiffness and shape adaptation mechanism at the physical human-machine interface of wearable device by integrating a soft pneumatic actuator, which is made of 3 chambers, 2 based on the layer jamming technologies and 1 empty to allow for inflation. So starting from a planar state, the system can be activated by stiffening the first layer jamming chamber, so the external one. Then the inflatable chamber is pressurized, thus pushing the inner layer jamming chamber on the residual limb, and thus adapting the inner interface to the limb shape. At the end, the new configuration can be freezed by applying the vacuum also in the second layer jamming chamber. So in our previous work, the 3 chambers were made of thermosealed plastic sheet, and we use 2 elastic band to lock it together the 2 layer jamming chamber, but allow for the relative movement required during the inflation. Now we have changed the design, and in the new system, the inflatable chamber is made of silicone gel to improve the achievable displacement of the system, and the layer jamming chambers are made of 10 sandpaper sheet overlapped and interlocked to 2 rigid parts, lateral parts that can be used also to integrate the actuator in the wearable system. And the sandpaper sheet are sealed within a silicone chamber, so the layer jamming actuator can be stretched also in tension direction without the need of the elastic bands. We developed also a wearable control unit which integrates a DC pump that can be used both as a compressor and as a vacuum pump by opening and closing 4 solenoid valves. The final weight of the system is 600 grams. And in this figure, you can see the final system with the wearable control unit positioned at the low back of the user and the actuator on the lower limb. And now as a future work, we are working on the integration of a pressure textile sensor in order to control the inlet pressure of the inflatable balloon on the basis of the pressure applied on the skin of the patient. So thank you for the attention, and please feel free to come to the poster if you have a question or suggestion. Thank you.
Thank you very much for this talk. We directly go over to the next one.
So hi, my name is Chris Dorsey. I'm a faculty member at Northeastern. And the purpose of my lab is to create tunable morphology, reconfigurable sensors through both structure and materials. So what I'm talking about today is a recent exploration of a 3D printed textile-like material that's a collaboration with Hiroshi Ishii's group at the MIT Media Lab in creating this tunable textile-like material and thinking about its applications for soft and wearable robotics. So we're using commercial FDM printers with commercial filaments and changing the print properties in a process called Defextiles, which was initially developed by student Jack Foreman at MIT. And so in Defextiles, the process kind of exploits stringing behavior that's an undesired property in a lot of 3D prints that are FDM 3D printed. We're exploiting the stringing behavior of FDM printers to create this extremely compliant material that can be tuned through the print process. So what you see on the right is a structure, just a cylinder that's being printed from 10 to 60 to 100%. That print took about 20 minutes. So initially this process was developed as thinking about developing at-home garments. So a designer could have a design in mind for a new shirt or a new dress, print it out using a 3D printer at home, and then have someone else try it on. So it's a rapid fabrication method for garments and accessories. And these are a couple of examples of accessories that we wanted to demonstrate. So a fascinator on the right using a couple of different textures of Defextiles, from very rigid to make up the hat and brim to very compliant to make up the nice ribbons at the end, and also an extremely compliant wristband with an RFID button on the end. So one of the things I'm really interested in with this Defextiles material is by changing the print properties. And here we're changing the extrusion multiplier, which is, you can think about it as the flow of the filament out of the printer, as well as the speed. We get completely different material properties. So what you can see in the two photos on the left pre-break and on the right post-break are how the material changes in morphology and changes its properties. So on the bottom, where we're using higher speeds, and lower extrusion multipliers, we get an extremely ductile material, whereas at high extrusion multiplier, low speed, this one, we get an extremely brittle, stiff material. That microstructure characterization is borne out by what we see in strain characterization to break as well. At the top, again, what you're seeing is low speed variations in extrusion multiplier, and we're seeing an increase in force at break, decrease in maximum strain that can withstand, whereas the higher speed devices have a much higher strain at failure. On the left, the curvature examples show you kind of the drapeability of the material towards textiles. Okay, so where is this going as we think about sensors and actuators for soft robots? So what I'm really excited about is the fact that we can also demonstrate this material with conductive filaments using something like protopasta that I'm showing you 3 samples of here. So those are the 3 protopasta sensors. We see similar tunability both in the electrical characteristics from a sheet resistance of approximately 5 kiloohms per square to less than 400 kiloohms per square. Same trend in mechanical characterization that we saw with the insulating filaments. We can also co-print using multi-head 3D printers, both insulating and conductive PLA, which will lead to sensors and actuators. So what's next for this project is we're looking forward to further investigating coating the textiles using silicone or sputtered metal to additionally functionalize them, and then applying these materials to soft fluidic actuators, as well as varying the material properties in the print with full control G code, which will allow us to have different regions of compliance within one print. We envision such developments as soft sensing actuators. All right, with that, I will thank you for your time. If you have any questions, I'll hang around during the poster presentation. Thank you.
Okay, thank you very much for this presentation. Now another one without a MacBook, that's good. Yeah,
okay.
Please.
Cool. Hi, I'm Crystal, and I'm here to present our work on a 4 degree of freedom origami fingertip haptic device with pneumatic actuators. So cutaneous fingertip haptic devices are wearable devices that apply forces and torques to the fingertip in order to allow users to interact with virtual objects. These devices are useful for applications such as entertainment, teleoperation, and training. So in order to render all forces and torques that your fingertip would experience when interacting with an object, the device would need 6 degrees of freedom so that it can render forces in X, Y, and Z and torques about these axes. However, as you increase the number of degrees of freedom that the device can render, you also increase its kinematic complexity. And this generally leads to an increase in size and weight. In addition to that, with traditional manufacturing techniques, this also tends to lead to increased manufacturing complexity as it increases the number of pieces that must be produced and assembled. So in our previous work, we developed a 3 degree of freedom device that rendered forces in X, Y, and Z. And this device was used in several studies where participants lifted and moved blocks within a virtual environment. However, we also noted that when users would begin to lose their grip on these virtual objects, they would begin to twist in their fingertips, and this 3 degree of freedom device was not able to render that twist on the fingertip. So with this observation, we then developed a 4 degree of freedom device that was intended to allow us to test whether adding this twisting degree of freedom about the Z-axis, so twisting on the fingertip like this, would allow users to better grasp and move objects within a virtual environment. However, after testing this 4 degree of freedom device, we decided we needed to double the force and torque output of the device in order to provide sufficiently compelling haptic feedback in order to conduct this user study. And so this led to a redesign of an overall redesign of the 4 degree of freedom device, including redesigning its structure and actuation scheme. And that leads us to the focus of our current work. So based on the findings from the first device, we began the redesign process. And this image that you see on the screen is an annotated version of our prototype, which outlines some of the force and workspace requirements. I'm going to kind of go through this just as sort of to foster discussion later on in terms of requirements for potential actuators for this kind of application. And this is also the device here, and I can show it to you at the poster if you're interested. So to summarize, the device needs to exert forces of plus or minus 2 newtons in X, plus or minus 2.5 newtons in Y, 3.2 newtons in Z, and exert a torque of about 10 millinewton meters to the fingertip. In order to sufficiently deform the fingertip, it also needs to be able to move plus or minus 5 millimeters in X, plus or minus 3 millimeters in Y, 6 millimeters in Z, and have plus or minus 45 degrees of twist. We found the bandwidth of the previous device to be sufficient and would like to maintain that minimum bandwidth of at least 9 hertz. And of course, we need the device to also have 4 degrees of freedom. And finally, we would also like to minimize the overall encumbrance when using the device by reducing its weight and size. So I wanted to talk a little bit about the design and manufacturing of the current prototype. So in order to meet these requirements and also overcome the manufacturing challenges that come with a high degree of freedom structure, we use an origami-inspired design. The main structure is made from layers of fiberglass and fabric that are laminated together with layers of adhesive. The fabric layer allows for flexible hinges in the structure that when folded together form a 4 degree of freedom delta mechanism that interacts with the fingertip. We also use pneumatic pouches and springs cut from polyimide to actuate the device, and those are adhered as a final layer. Once this entire stack is assembled, the prototype can then be folded together and put on the fingertip. So on the left, you can see a GIF of our most recent prototype moving the tactor in X, Y, Z, and theta. Right now, this device is actuated with pneumatic pouches. The pouches are manufactured through heat stamping layers of TPU-coated fabric, and the stamps are 3D printed with an SLA 3D printer using a high-temperature resin. Unlike typical pouch motors, these pouches are used in an accordion configuration with an antagonistic spring acting in the opposing direction, and this allows for bidirectional actuation. While this method of actuation will allow us to meet our requirements, the pneumatic air supply lines and offboard pressure regulators do decrease user mobility and overall portability of the device. And so we're particularly interested in talking about other actuation technologies that can help us meet the device requirements that I mentioned earlier within a smaller, more portable form factor. And so greatly look forward to hearing your thoughts on other smart material-based actuators that could be used for this application throughout the course of the workshop. And if you have thoughts on this or would just like to talk more or come see the prototype, please come visit us at the poster session. Thank you.
Thank you very much. That was working good. I hope our next presentation is not a MacBook. No, it's not a MacBook, right? Perfect. So please come ahead and
Hi, my name is Janis Jakubov. I'm a postdoc working with Professor Alison Nakamura at Stanford. And today I'm happy to share our ongoing work on voxels. It's fully 3D printed soft multi-contact haptic voxel displays for enriched tactile information transfer. So our work is in the field of haptics and then building haptic robots. And our skin is actually a nice organ which embeds a lot of mechanoreceptors that enables us to interact and feel the surrounding environment. And these interactions are due to the skin deformations such as lateral, rotational shear, pressure, vibrations, and so on. This skin is actually allows us to build various haptic devices that could allow us to connect with the virtual world in the virtual domain. And wrist-worn haptic devices especially allows us to attach them on the wrist, which has the large real estate and build really like multi degrees of freedom devices. And as you see, there was a lot of work in the literature on having the traditional mechanisms which face miniaturization and encumbrance problems. Later on, soft robotics actually tried to can achieve high degrees of freedom by combining these soft actuators as well as rigid components. However, those devices had single contact interaction. So later work on dielectric elastomers, shape member polymers, and smart materials in general allowed to build kind of haptic pixels that could be distributed on the skin and provide a very complex haptic stimulation to the body. The problem is that we try to address address the questions: how can we actually build a multi degrees of freedom skin deformation device, as well as kind of distributed on the skin to achieve the multi-contact, so we can increase the information transfer. And also that kind of brings another problem where we would like to scale them up, but how are we going to kind of address the manufacturing question here? So in here we introduced the monolithic 3D printing process for achieving high degrees of freedom, multi-contact soft material device. So so the device we introduced today is called Hoxels. And this is the very initial prototype, which has two haptic voxel components, which can actually produce a lot of different interactions like skin shear, stretch, squeeze, twist, as well as vibrations. And the device is entirely printed monolithically, but still, yeah, I have to mention that due to the limitations of the workbed, the Formlabs 3D printer, we had to kind of print the device in two pieces. Like the wristband was printed separate and then attached to the haptic unit. The unit has bellow type of actuators that compress selectively, and that compression actually moves the platform on top, and the tactor in the middle is attached to the platform, and that tactor actually interacts with the skin. And we can increase the number of these haptic voxels to have multi-contact interaction with the skin. And the device is also embeds microfluidic channels. It's pneumatically driven. So especially like, in this prototype, we drive it using vacuum. In placing multiple of these voxels, haptic voxels, can generate very different versatile motions. So you can imagine that the two pins which move independently, they can move in the same direction for shear, for instance, or in the opposite direction to have twist or squeeze of the skin. And here we could see the video how these pins, they actually come out from the housing and start to move and interact with the skin. So we measured the forces in the blocked state for the maximum vacuum pressure, and for a single tactor actually generates plus minus 1.6 Newton, and an enormous force actually in the Z direction because we actuate all four actuators. So so our method is also extensible to other parts of the body. Earlier we demonstrated the device application on the fingertip, which is called fingerprint, and this device actually moves in 4 degrees of freedom. I couldn't play the video, sorry, but I have the prototype and videos if you would like to see in our poster. Thank you.
Hey, thank you very much. The last presentation of this short abstract presentation session is online. So do we have...
Okay, hello, I'm Samuel Yusuf, research assistant at the Biohybrid Soft Robotics Lab at my university, Egypt. And I'll be presenting our work on the design and control of soft biomimetic robot using a Finray actuator and reinforcement learning. So this is part of an ongoing project with a motivation is to develop underwater robots that can be deployed in marine environments without harming the ecosystem or disturbing it, and monitoring stuff like coral reefs and so on. So our approach could be divided into 3 stages mainly. I will talk briefly about each stage. So first, we took inspiration from the actual fish. We studied the structure of the fish body and the motion of the swimming motion. As you can see here, we track the different parts of the fish, and mainly to track the frequencies of the tailbeat of the fish. Here in slow swimming, I will forward the video. You can see in medium swimming, medium speed, and in fast swimming. After that, we try to design the robot based on the analysis of the fish, by taking the same proportions of the fish and the same shape of the fins. So we try to use the fin ray effect, which is patented by Fist. The main concept, how it works, it's mainly this triangular shape with the sides being flexible material and membranes and connectors membranes in between. And when force is applied on the actuator, it bends in the direction of the applied force. So we tried to incorporate this in our design of the robot, and activated using a simple servo motor. The tail was manufactured using an FDM printer. It's made from flexible TPU materials, but we are currently investigating other materials like silicon, Ecoflex, and different activation methods like shape memory alloys and so on. So after this, we also, depending on the frequencies that we got from the fish analysis from before, we defined a set of actions or a set of different speeds for the tail to oscillate, to create different speeds of the robot. As you can see here, I'll forward the slide a bit. This is some of the faster speeds, and this, as you can see here, more slow swimming. So the third stage is to teach the robot to perform a more complex task. So we use reinforcement learning. Briefly, reinforcement learning relies on having an agent-based robot interact with its environment through different actions, and we observe the state of the robot, the new state of the robot after the action, and based on the state, we either give it a reward or a penalty. So our setup here, the training starts by the robot having random actions based on a greedy policy to manage the exploration and exploitation of the environment, and the state is tracked. Then the algorithm, the RL algorithm, gives it a reward or a penalty. Our reward is based on the task we wanted to achieve, which is having the robot reach a certain task, a certain target in the tank, predefined target. So it's proportional to the distance between the robot and the goal. So we trained three different reinforcement learning algorithms: PPO and proximal policy optimization, actor critic, and deep Q learning, mainly for 25,000 steps. That was initial training, and we observed the performance of the three algorithms, and chose to continue the training as with the PPO algorithm, as it was the more stable of the three. So we continued the training of the agent for more 25,000 more steps, and this is the video of a test run showing the robot reaching the goal, the first goal here, the red one. And then an additional reward is given to the robot when it reaches the defined goal. Then the goal is changed to the other target, and robot will try to go to the other target. So that's it. And I would like to thank you, my colleagues, the team, and our sponsor. And that's all. Thank you. Unfortunately, we couldn't be in person, so you could contact us through my mail or the lab's mail. Yes.
Thank you very much for this presentation. Again, please feel free to approach the authors of these extended abstracts online or here in person. And now I'm very happy to release you